Well, hello, calculus people. How are you feeling today? I hope you're doing all right, because we are about to do day 2 of 3 of vectors. Today we're talking about vector-valued functions and how we can do some calculus on them. So very, again, cut and dry. Nothing too insane. Just what's a vector-valued function, how do we use it, and how do you apply some techniques of calculus to it, which basically means integrations and differentiations. So here's what we're going to do. We're going to practice our plane curves by sketching this graph of the vector 5 minus t square root of t. And vector valued functions are just like parametric equations. That t we consider almost a time. There's something that's in motion. So the idea of this would be at some motion of time, we have the vector's x component and the vector's y component. So really what we're doing is we're tracing the plane that is created by these vectors. So if t is 0, then I get 5, 0. If t is 1, I get 4, 1. And we'll do a nice easy one like 4. Then we have 1, 2. So what does that give us? What kind of an equation? See if I can do these axes somewhat straight. Probably not. So I'm just going to take a line tool. Oh, well, look, a dotted line. Well, that'll work. That's okay. There's our axes. So 5, 0. We got it right there. 4, 1. Right about there. 1, 2. Right about there. Well, maybe one more point to see where we're going here. So why don't we go and put in 9. 5 minus 9 is negative 4, and then the square root of 9 is 3. So negative 4, 3. 1, 2, 3, 4, and negative 3. All right, so we've got a graph that's going like this. Now I put an arrow there, but I have to be careful because we have to talk about direction. Now the direction is easy to see. We have 0, 1, 4, 9. We know it's traveling this direction. So that's important for a vector-valued function. We're tracing the path the vectors are taking. So really what you have is you've got yourself a whole bunch of vectors that we're putting together. So like the first vector is 5, 0. The second vector, the third vector, the fourth vector that we did, and so on. You know, we skip numbers, so I'm not saying that's the first, second, and third vector, but the ones that we graphed. So every spot on this graph represents a vector along this equation. Okay, so that's how you graph vector-valued equations. Now the graph actually stops there because we'll talk about domain. The domain of this function is, well, t cannot be negative. So therefore, the domain is t has to be greater than or equal to 0. And that's built into the problem. You cannot have the square root of a negative number, or you have imaginaries. So that's the graph of the vector-valued function. Now, what if I take a rectangular equation and make it into a vector-valued function? Now you know this particular one. It's a line. It's a very strangely written line, but it's going to be a line. So there's a couple ways to write this vector-valued function. For example, the easiest way is to let x equal t. And then all you do is you take the equation and in place of x you put t. Let me just solve this one for y. It would be 1/3 2t plus 5. So you could write the equation as a vector-valued function of the x value being t and the y value being 2t plus 5 over 3. Now this is not the only way to represent this as a vector-valued function. No, you have an infinite, actually, number of answers. You can let things equal anything. What I mean by that is, let's take this equation. I'll do another one. This time I'm going to add 3y to both sides from the beginning. So now I'm going to let t equal 2x plus 5. which means that I'm going to substitute 2x plus 5 for t. T equals 3y. So if I solve this equation, I get y equals t over 3. And if I solve this equation for x, let's see, I get t minus 5. So it would be t minus 5 over 2. So another way to write this equation, same equation, the x component would be t minus 5 over 2, and the y component would be t over 3. Now how can these be the same graph? Again, the t's are the key. It's not the same vector valued equation. It's the same representation of a rectangular graph. What I mean by that is, let's pick a 0. If time equals 0, then r sub 1 would equal 0 5/3. So at time 0, this vector is going to be 0 5/3. Now that's not going to happen here. For r sub 2, let me just put it down a little teeny bit. For r sub 2, if I want to get this same value, I have to let t equal 5. If I let t equal 5, I put 5 in here. 5 minus 5 is 0. 0 over 2 is 0. 5. So you see, I generate the same points with both of these vector valued equations. It's just they're not the same equation because they happen at different times. Okay. It's the same path, but they happen at different times. Both of these answers are correct though, and like I said, there's an infinite number of answers. You can let anything, you can substitute t for anything and just solve for x and y. Okay? So these are both good, and whichever one you like, that's up to you. With vector valued equations, all the things we do in calc are really pretty much exactly the same. If I want to find the limit of a vector value equation, I just find the limit of each component part. That's it. The limit is of t approaches 0 v to the t will be e to the 0, which is 1. That's a nice and easy one. Here, a little trickier. You might remember this identity, but if you don't, good old L'Hopital's rule will take into effect, because we get 0 over 0. So the derivative of sine is cosine. Derivative of t is 1. Now I can plug the 0 in, because the cosine of 0 is 1. Continuity, another big issue in calc. Just determining intervals where this is continuous. Well, you got to deal with both issues. The x component and the domain of the x component would be that t has to be greater than or equal to 0. The y component, whoops, that's pretty ugly. So the y component, t would have to be greater than or equal to 1. So really we're talking about the continuity with the time. At what times is this vector valued function defined? So I have to look at both of these and choose the one that's defined all the time. For example, I can't say t is greater than or equal to 0, because if t is a half won't work in here. So for the entire vector valued function, the domain has to be this. So it's continuous when t is greater than or equal to 1. All right, here's what we're going to do. We're going to take this vector valued function. We're going to graph it. Then we're going to graph the one particular vector art of 2 and the derivative of the vector valued function at 2. Now, how do we want to graph it? Do we want to put t values in and sketch it? Do you want to turn it into a rectangular graph, it doesn't really matter. I think I might try that. I know that the x component is 3t, which means, of course, that x over 3 equals t. I know the y component is t squared minus 2. So if I plug in the t, which is x over 3, I get this parabola, which would be x over 3 squared minus 9. Should be a pretty easy one to graph. I'll pick a couple points. We'll graph it. Wow, I said minus 9. My brain is going. It's minus 2. Ooh. So 0, negative 2 is the vertex. If I plug in 3, I get 3 over 3, which is 1. 1 squared is 1. 1 minus 2 is negative 1. And this is symmetrical on the other side, so negative 3, negative 1. I'm going to pick 6. 6 over 3 is 2. 2 squared is 4. 4 minus 2 is 2. So 3, 4, 5, 6, 2. 4, 5, 6, 2. And so we got room, we'll do one more. We'll do 9. 9 divided by 3 is 3. 3 squared is 9. 9 minus 2 is 7. So 9, 10, 8, 10, 9, 8, 7. Oof, there we go. Now I'm going to try to draw this curve, which is not going to be the easiest thing for me to do. Wow, I fit that side pretty well. Now let's see how badly I mess this one up. I didn't do it too bad. And I think one of the reasons it wasn't too bad is because I wanted to make sure I had a perfect graph for the next part of it, so I graphed this on Desmos. So my graph wasn't that bad. Go back and forth, it's pretty good. I was pleased. Anyway, the reason I did it this way is because I want to show you now about these two parts. So the vector evaluated at time equals 2, at t equals 2, would be 6, and what, 2 squared would be 6, 2. So that vector valued function, which is represented by this curve, oh, it didn't put a direction, but I know it's going this way. Because I know when t is 0, we're here, and I know that when t is 2, we're going this direction. Okay. So if I draw the vector 6, 2, we start at the origin, and right there. Notice how I did the one point in orange just to differentiate from the rest. I'm having a real hard time getting it just exactly. Okay, so that's your vector 6, 2. Now we're going to take the derivative of this, and the derivative of a vector function is just like a derivative of all the other things. Derivative of each part. What's the derivative of 3t? 3. What's the derivative of t squared minus 2? 2t. I'm going to plug in 2. I'm going to get the vector of 3, 4. Now I'm going to graph the vector of 3, 4, but I'm going to start it at the end of 6, 2. You're going to see why. So if this is a vector of 3, 4, it means I'm going to go over 3, 1, 2, 3, and up 4, 1, 2, 3, 4. Now, what this is going to do is this particular vector is going to be a tangent to that curve. All right? So this particular vector, the vector 3, 4, is tangent to the vector valued function at the vector of 6, 2. All right? Let me get that out of the way, because that vector can be moved anywhere. But this vector is tangent right there at 6, 2. That's what the derivatives of vector value functions can tell you. All right, that makes sense? All right, let's see. Derivatives. Look at this. Again, derivatives are just like normal. You just take them. So the derivative of t squared plus t is 2t plus 1. That's the x component. The y component would be 2e to the 2t. And we can just go on and on like that. The second derivative is 2. This would be 4e to the 2t. And there's your higher order derivatives. We can go on and on and on. So derivatives are pretty straightforward. Same with integrals. This is the integral of 7 over t dt, and the integral of e to the 2t dt in vector form. So this would be the natural log, 7 natural logs of the absolute value of t plus a constant. And what is this? 1/2 e to the 2t plus a second constant. Now you can actually write this a different way. This c1 and c2, when you add these vectors together, you're adding a constant to the x and a constant to the y. So together the vectors are being added a constant value. So you may rewrite it like this. Plus just a big constant on the outside. All right, last one. And a definite integral. Well, it's the same exact thing. We're going to go from 1 to 4 of t dt, and from 1 to 4 of square root of t dt. So let's see what we got. This would be 1/2 t squared from 1 to 4. This one would be 1/2, so you raise it to 3. So 2/3 t to the 3/2 from 1 to 4. So let's see, we've got 16. So 8 minus 1/2. And let's see, plug in 4. Square root of 4 is 2. 2 cubed is 8. 8 to 2 is 16. 16/3. Plug in the 1, you get 2/3. So this vector valued integral would be 15/2 and 14/3. Ladies and gentlemen, that is how you do some calculus on the vector valued functions. Now remember, right now we're just delving into the vector valued functions in this stuff, not real deeply, but just enough that you need to know for this class. You're going to get into them a lot more in Calc 3. That's why you need the basic idea of how they work. So hopefully, you found this a nice way to end the year, something not too strenuous on the brain. We'll have a live meeting on Thursday, which would be May 28th. After that, we have one more vector to go, and time permitting, we'll do 2 polar ones, and we'll get those done pretty easily. And just remember that all the assessment problems I'm sending you, they're just due by June 5th. So I hope you guys have a wonderful, wonderful day, and I will talk to you later. Bye.